Hello, everyone. Hello to all our attendees, and thank you very much for attending day two. And I hope you really enjoyed yesterday. So to begin this wonderful day, it is with special excitement that I'm pleased to welcome our first keynote speaker for the day, Ulrich Paquet. So he comes from DeepMind from United Kingdom. Ulrich is a South African research scientist at DeepMind who lost his heart somewhere in the Bushveld and is always looked for ways to find it. His most expedition in this quest is with the deep learning in Daba and its community of hardworking, dedicated friends and peers. He holds a PhD in machine learning from the University of Cambridge, lived life on the edge in two high-tech startups, managed a team in Apple, and with Naomi Koenigsson developed the core of the Microsoft recommender system. He was in the initial Xbox One team and is still itching to build the next big thing. So thank you very much for your humbly accepting our invitation, and welcome. The floor is yours.
Thank you very much, and good morning, everyone. Good morning, MoroccoAI. Thank you very much for having me. I'm going to spend the next hour talking to you about the history of artificial intelligence, and it's a long history, and I'll tell it through the lens of AlphaZero and chess, because I'm also a chess player. And the title of my talk is AlphaZero and Going Beyond, an AI Journey Through Time. So the first part of this talk is just about AlphaZero, reinforcement learning, AI, and chess. So let's talk about chess. Chess is an ancient game. Here's a picture from the 1200s, and from an ancient Spanish book showing two noblemen playing chess. And in 800 years of development, we've reached a point where chess is almost a well understood and very almost solved game. And it's crossed paths with artificial intelligence many times. My first experiences with artificial intelligence wasn't as a researcher, it was as a youngster, as a chess player. And I had a machine like this. It was called the Kasparov Chess Trainer, and it was symbolic. It ran minimax search trees internally. There was nothing advanced by today's standards. When I was a child, this event happened. It was Garry Kasparov, who was the world chess champion, playing against IBM Deep Blue in New York. It's a six-match game. And Garry Kasparov, one of the greatest chess players who ever lived, lost against this mega machine that IBM built. And I remember that I was sitting in my room in South Africa wishing that I could have been part of the action in New York in the late 90s. It's a very pivotal moment in the development of artificial intelligence and also in chess. But the techniques that IBM used are very much the same techniques that people were thinking about in the 1950s and 1960s. And chess has always been what I call a petri dish for artificial intelligence. So many AI techniques are developed in the domain of chess before it gets pushed to the real world. It's because chess is a fully observed game. It's a zero-sum game. There are no hidden states, and that's been the history of chess as a petri dish. And chess as a petri dish has spanned many years. So there were many ideas and many ideals through the centuries. I'll just mention a few. So in the 1770s, von Kempelen, he was a Prussian Austro-Hungarian, developed the mechanical Turk, which I'll tell you about in a second. It was a mechanical machine with a human hiding inside that could play chess. Fast forward to the post-World War II era with Claude Shannon at Bell Labs. Claude Shannon in 1949 wrote a paper called Programming a Computer to Play Chess. And it's a fantastic paper that introduced, I want to say all, but many of the key concepts that are currently used in modern chess engines. Minimax search, the idea of an evaluation function, etc. Next big moment was in 97, at least in my recounting of history, where the first human world champion lost competitive match against a chess machine. Then came 2016. So in 97, people thought the world champion lost against a chess computer. But Go, the ancient Chinese game, is so much more complicated in terms of its branching factors. It's exponentially more complex in terms of evaluation that it will be many, many years before an AI machine or system beats the top human players. And then 2016 was the moment when Lee Sedol lost against AlphaZero, DeepMind's Go playing agent. And if you want to know more, you can watch the AlphaGo movie for free on YouTube. I highly encourage that. It's really entertaining. But let me take you back to the 1770s. So this is what AI looked like before computers. So the mechanical Turk was a machine with a puppet that could be controlled with mechanical sticks and levers. And it had a box underneath with an intricate array of mirrors. And a very small person would climb inside and hide and then make the moves. And the arrangement of mirrors was such that no matter which door you opened, the person could slide back and forth, and you'd never be able to notice that there was actually a person hiding in this box. So in the 1770s, this AI traveled the world. It toured the imperial courts of Europe, and famous people lost against it. So what do these two men have in common? This is Benjamin Franklin of the US on the left-hand side and Napoleon Bonaparte. These two great leaders both lost against an AI, well, artificial intelligence. They both lost chess games against the mechanical Turk. But that's far history. I want to take you to the year 1953, and I want to read a few things from papers that I found in Alan Turing's archive. So this is a paper that Alan Turing authored. It's called Digital Computers Applied to Games. And I'll just read a few things from the thinking 70 years ago. So Alan Turing asked, could one make a machine to play chess? Of course, the answer is yes. Then he said there are several possible meanings which might be given to the words. And then he said, could you make a machine to play chess? 1, 2, 3. And then he follows with point 4, which is a very interesting question. He said, could one make a machine to play chess and to improve its play game by game, profiting from its own experience? And then he said, to these we may add further 2 questions. These are unconnected to chess. And then question 5 is the interesting one. He said, could one make a machine which would answer questions put to it in such a way that it would not be possible to distinguish it from the answers of a man? And of course, question 5 is what we know now as the classic Turing test. Question 6 was, could you make a machine which has the same feelings as you and I? And then he has a few answers. His answers is to questions 4 and 5 about the Turing test and about a self-learning chess machine. He says, I should answer, I believe so. I know of no really convincing argument to support this belief, and certainly of none to disprove it. So in the next part, I'll tell you about question 4, building a machine that can teach itself to play chess and improve its play game by game, profiting from its own experience. So traditional chess engines, in the way Claude Shannon devised it, had many hand-coded rules and it did manual feature extraction. I want to call this the craft of handcrafting. So you as an engineer would design an evaluation function that looks at the chess position and tells you who's winning and who's losing. And it requires a lot of craft and expertise. AlphaZero as a system replaces all the traditional handcrafting minimax search with 3 things. It replaces it with learning, neural networks. It replaces it with a different kind of search, and it replaces it with a mechanism of self-improvement. So learning plus search plus self-improvement. If you want a Christmas present and you have no idea what to buy for your friends, there's a nice book called The Game Changer by Matthew Sadler and Natasha Reagan that tells a bit of the story of the games that AlphaZero plays. So learning plus search plus self-improvement. So how do these work? Just before we get there, AlphaZero sits halfway between top chess engines and top humans. So top humans will evaluate hundreds of positions when they make a move. Top engines will evaluate millions, and AlphaZero possibly tens of thousands. So we're not quite at the level of human AI, human compute power, but it's a big step, an interesting step closer. So AlphaZero, I mentioned, has a learning system, and it's an adaptive, self-improving system. So my high-level view of developing machine learning systems that learn by themselves and self-improve is the following flow diagram. An adaptive, self-improving system should always have a component that learns. There should be some component that makes decisions. There should be some part that changes the world, and then there should be some part that improves that improves data and feeds better data back into the learning system. And then that should become a cycle that allow you to self-improve. So what does this look like in a neural network chess playing system like AlphaZero? So let's start with a big pile of chess games and with data. So let's start with learning. That's the first step. That's the first component. So imagine someone gives you a massive pile of data. In this case, it's chess games. The chess games could be completely random. They don't have to be amazing. But every game has a few things. It has positions, which we call states, S, and will have a game outcome, which we call Z. Tells you the game outcome is just who won, lost, or draw. So in this position, state S, white could have ultimately won, and Z would have been 1 instead of -1. The second component in this data is okay. So let's just speak about the game outcomes. So we learn a neural network to approximate the data of game outcomes. So we learn a neural network which will approximate the value of the game, and it has to generalize. So the network will take in a state, board position, and then emit or predict the expected probability of winning the game from that position, just from data. It's very easy to do. It's just a regression against 3 targets, -1, 0, and +1 from an input position. It's almost like computer vision with a 3-class problem. Okay, so you can do that. The second kind of data there is from a position. There's not just the game outcome. There's also the next move that someone played. So every state leads to another state by playing an action. So the state leads to the next move or action, and that goes to the next state. So there could be a multiple number of next states depending on the move you play. The second neural network that we'll learn is a neural network that takes in the state and then predicts a probability of how likely every action is from data. So there we go. It's a policy network, and it should be able to generalize, and it just has a weight that sums to 1 across all possible legal moves. So now we're equipped with 2 neural networks, which I'll tell you a bit more about later. Now we need to make decisions with those 2 neural networks that we've learned so far. We make decisions with something called Monte Carlo tree search. So we start with the state, the position that we want to evaluate. We evaluate it with a policy network and eventually roll out. And I'll tell you a bit more about the process in a few slides until we hit the leaf node, and then we evaluate it with a value network. And this is done over and over again until finally one specific action is played or simulated more than any other action. And that is then the move that you make. So this decision-making part has many connections to multi-arm bandit, for instance, where you try to pull different arms or experiment with different moves until you get the move that has the highest payoff. There's also in reinforcement learning a trade-off between exploration and exploitation. So in this case, you want to simulate all moves at some point so that you're sure that you don't miss a good move, but you want to simulate the better moves more. Okay, so we've done Monte Carlo rollouts, and there's one move that we like a lot. We've simulated it more than others, and that's then the one we play. So we'll play that move, bam. So if you look at The action value Q estimate, and the thick arrow is the bishop that moves to square G5, and bam, we play that move. So that is now a new state in the game. We've changed the world. We're actually playing self-play games here. If we do that over and over again, play a number of such games, we've used our neural network plus search to change the world, and that gives us better data or better games. So what we end up with is a new pile of games that look better or are of higher quality than the first pile of games that we started with. And then this loop just continues until the network gets better, the quality of games that we learn from get better, etc., etc. Okay, so that's in a nutshell an adaptive, improving, self-improving system. That's AlphaZero. So you're probably asking, please tell me the details. Like, I like to code neural networks. So let me tell you a few details. So I mentioned that the network has two parts. There's a value network and a policy network. I'll just briefly mention what these two look like in practice. So here's a little diagram. It is ResNet with multiple blocks. I'll just start at the very bottom. There's an input, which represents the board. And then that goes through a number of ResNet blocks that are stacked convolutional layers until you hit the top of what's called the torso. And that network would then have two heads. One would then have a few layers that would predict who's going to win or lose. And the second part from the torso would predict, after a few layers, what the possible next moves could be. So it's got the policy head and a value head. And that massive neural network is trained with gradient descent. A bit later, I'll tell you about what each of these different blocks encode in practice. So for now, just assume that there are 20 ResNet blocks stacked on top of each other that extract interesting features, and these then go into the policy and the value head. There we go. How does decision making work in this case? I'll just dive into Monte Carlo research just a little bit. So this is MCTS for you. You start with a state, you evaluate it through the policy network, and you get a probability for every next move. That then goes into a rule. And the rule combines an action value estimate, which I'll tell you a bit later, and a term that accounts for exploration. And then you take the maximum action. So I'll tell you a bit about the formula later, but I'll pick the maximum action and bam, that's the next move that I make. I repeat this process until I hit a leaf position. And at the leaf position, I call another neural network to evaluate it. Once I have the evaluation, I need to do a backup up my search tree, and that backup looks like this. So we need to back the value up to the top, to the root node, and the backup says, I keep three things on an edge. I keep the sum of the values that I've backed up. I keep a counter of how many times I've backed something up at the edge, and I keep the action value estimate. So here goes. I start from the bottom, and I just add my evaluation to the sum. I increment my counter by 1, and I normalize to get my action value estimate. And then I do it for the incoming edge until I hit the root. So that means that I have a search tree that has a number of counters along different edges. And those counters are important because they will be used to trade off exploration and exploitation. So this means we're done with one MCTS simulation. So now we need to do this hundreds of times over. So we start again. Now let me show you a few more important bits. The decision-making rule is from something called the PUCT algorithm. There aren't many important things that you need to take home from this, but here are two. The first one is that you want to bias search towards actions that are more likely. So the prior goes into the U term. So higher values for the prior means you're more likely to they're more likely to be the maximum. The second term has a count, 1 over a counter of the number of times you've actually gone down that path, and that just ensures that eventually all arms or all possible moves would be explored if you take the limit up to infinity. So that's decision making. So we repeat this. That goes into the argmax. You pick the maximum action again, get to the root, bam, back up, and then after many MCT simulations, there's one path that you've chosen more than others, and that's the move that you play. I know I'm going through this quite fast for an early morning talk, but I just wanted to give you a flavor of how search works in Monte Carlo research. Okay, that's the move we played. We get improved data. So I want to say a few words about artificial general intelligence, because in chess, you observe all the pieces on the board. The real world is a lot more nuanced than this simple schematic petri dish system that's chess. That's very well understood. If I were to give a talk from the stage, you might be yawning in the background. There might be very complicated signals that I should receive and interpret. I might not even be able to see you, so there are many hidden states. And that makes this loop, the self-improving loop, a lot more nuanced than it is in chess. And that's like the big challenge that we'd like to solve beyond chess. Okay, so let me tell you a few more interesting things. So what concepts does AlphaZero learn? So AlphaZero, I mentioned, has a neural network inside that has multiple layers, and it tells you who's going to win or lose, most likely from a certain position, and what a good next move would be from that position. So we may ask, does AlphaZero learn anything or encode anything that's remotely like what a human would encode? Like, does it actually encode any human recognizable knowledge, or is it just complete gibberish and we have no idea what it's doing? Interesting news is that we do have an idea what it's doing. So let me tell you how we can figure out what concepts AlphaZero learns. So some questions we might ask is, does AlphaZero learn human recognizable concepts? What is it? When does it learn those concepts? Early in training, later on in training? Is there a sequence to knowledge acquisition? Do you need to master some concepts before you master other concepts? Is it in any way remotely like humans learn chess? So let's do an experiment and see if we could find that out. So there are other chess engines, notably Stockfish, that encode different human concepts. So a chess engine evaluation function, at least a typical one, would take a chessboard and it would decompose it into specific concepts. And a concept is something that has value or contributes something to the evaluation of the board. So for instance, you might want to know whether you're ahead in material or if you're behind in pieces. The evaluation function might contain a contribution that tells you whether your pieces can move a lot more or are more mobile than your opponent's pieces. It could have a more abstract notion of threats, like whether you can possibly capture a number of opponent pieces and they can't capture you back, for instance, and so the list goes on. So in a classical chess engine like Stockfish, although Stockfish already now has a neural network component, in a classical version of Stockfish, there would be a sum of evaluations for a chess position, and that would give you the total score. So we implemented a number of custom concepts, and we've taken a number of Stockfish concepts. And now we have a way to label many, many board positions with a concept score, a human concept score, like automatically. So now what you are interested in is whether any of these human concepts are represented in the 20 ResNet blocks. That's AlphaZero. So here's one way we could do it. So we take a chess position, we label it with a function, evaluation function that we write, a different kind of chess engine. And then we see if that data correlates in any linear way to the activations at a certain block. So let's say this is block 10. So we'd learn a linear regressor for block 10 for all the activations to try and predict the a specific concept like total score. So of course, if you've ever done linear regression, you'd know that the R squared, or coefficient of determination or correlation, if that's high, if it's like 1, then your output is really easy to linearly predict from your input. If it's 0, it just means that there's just no correlation at all. There's no structure preserved. So for an activation layer, we care about whether it preserves certain structure. So we get the R squared score for block 10 for a specific concept, for a specific checkpoint or point in the training sequence of AlphaZero. And now we do that for all the blocks in a specific checkpoint. So what you see in this graph is that as we go from block 1 to block 2 to block 3 to block 4 in these ResNet blocks, the idea of total score gets better and better and better encoded in the network up to layer 20, and the encoding persists through the network. And now we do this process over an entire AlphaZero training run, and you get a little figure that looks like this by iterating over checkpoints. And let's fill it in. There's the figure. So this tells us how well a certain concept like total score is represented in the AlphaZero network, where in the network is represented, and when it is learned. And it's very interesting that if you look at this picture, for instance, AlphaZero is most correlated with Stockfish's total score, not at the end of training, but halfway through training. And it's known anecdotally that AlphaZero plays different kind of chess than Stockfish. It's interesting that there's a sort of a convergence, and then there's a bit of a split as well. Okay, so we can do this process again, and now we pick a different concept like material, and we'll get a different plot. And we call these plots what, when, where plots. So what, because it's what concept is represented in the network. When is when in the network's training cycle, which is this long reinforcement learning, self-improving systems training cycle, are the concepts learned, and where are they learned? As in which layer of the network are the concepts encoded? Are they encoded in the early layers, middle layers, later layers? And then you can interpret these results. So you'll see, for instance, that for the total score and for the threats, AlphaZero correlates with Stockfish, and then the correlation drops. If you look at the threats concept, for instance, it's more represented earlier in the network than it's represented later in the network. If you take a few other concepts, like whether you have a threat of checkmating your opponent or vice versa, that's actually encoded all the way up to the last layer. And then the knowledge of whether you have a checkmate threat is not dropped from your network at all. So that's one thing that you could do. And it shows us that there are human concepts, actually many, many recognizable human concepts that AlphaZero learns over time. And it starts with zero correlation, and then these appear automatically, which is like really actually pretty amazing. A few more points, like AlphaZero and Stockfish doesn't have to have the same evaluation because they're different chess engines. So I'll just give you a quick example. So when you run a traditional chess engine and you run search and you get to a position that's not resolved, for instance, you're halfway through exchanging pieces, the chess engine would just continue expanding the position until things settle. AlphaZero, on the other hand, with Monte Carlo tree search, always simulates up to a fixed ply length. So if you are halfway through an exchange of queens, and you need to capture someone's queen, which is the major piece on the board, back, AlphaZero has to encode some look ahead, which different chess engines don't. only because the evaluation is different. And you actually see it in the residuals of this R squared value. So whenever whenever through linear regression we can't predict Stockfish's evaluation very well, it means that there is some substantial difference in the chess engines, more likely than not. And in all the outliers, if we look at all the outliers are always halfway through queen exchanges on the board. So on the left are the outliers, and we can map them back. So it's interesting that there is a reasonable explanation for this. There are many other things you could do. You could take a traditional chess engine's evaluation, and you could see how Stockfish, how AlphaZero's evaluation for position decomposes into piece values, for instance. So let me put it differently. If you learn how to play chess as a beginner, someone tells you that a queen's roughly worth equivalent to 9 pawns. A rook is 5 points, 5 pawns. A bishop is 3, and a knight is 3, and a pawn is 1. So if we just take the piece differences and we try and regress the AlphaZero network evaluation from it, you get roughly the same relative piece values. AlphaZero learns that the queen is worth roughly 9 points, rook's worth roughly 5 points, bishop and knights are equally valid over training steps. It's very interesting to see how AlphaZero's evaluation or value function decomposes or regresses as a sum of different Stockfish evaluations. So for instance, very early on, AlphaZero learns in this case that material is extremely important in training steps. This is after 10,000 training steps. It's like, yeah, I know. I need to keep hold of my pieces. Then over time, the relative importance that AlphaZero gives to material diminishes, while more importance is given to concepts like space and material and king safety and all these other more nuanced concepts. So it's interesting to see that you could actually regress this out of the training run. And there is some circumstantial evidence that there is a sequence by which knowledge has to be acquired. You first have to learn material value, and that has to as a network before you can learn any of the more complicated concepts. And the other things that I'll allude to in a paper that I'll mention a bit later that I'm not showing in this talk. Okay. The other question we might ask is, does AlphaZero learn anything like humans do? So here is the history of the first move that's played in a chess game from the late 1400s all the way to 2020. There's almost 500 years of data. And what we see here is that humans from the 1400s prefer to play the pawn in front of the king by 2 squares, predominantly. And then in the 1930s, other moves became slightly more popular. But it's very much like this. It's a one-trick pony. You've got one first move, and then slowly people realize that other moves are also really playable as first moves. Now, contrast this picture of human history, which says, hey, I can play one move, and then everyone follows the leader, to the way AlphaZero learns. So here's AlphaZero's learning trajectory for 3 different seeds. Over 1 million training steps. AlphaZero says, hey, I'm not going to do the human thing of like playing one move that everyone likes and everyone follows suit. I'm going to literally play every imaginable move almost equally for the first 20, 30,000 training steps. And then from there, narrow down my opening repertoire. So humans seem to add, AlphaZero seems to prune away until it narrows down to a very good superhuman playing style. Okay, so that's an interesting comparison between the two histories, AlphaZero history and human history. Okay, this one I'll skip. One can also do unsupervised concept discovery. So here are just a few examples of what you could do from the activation layers and non-negative matrix factorization. So I'll just explain the pictures to you. So there are factors that are encoded in these activation layers that tell you which possible diagonal moves could be made. It tells you what potential good squares could be to move to, or safe squares. it could count all the potential moves that your opponent could make, etc. So these are like the principal factors that are encoded in different layers. I'll skip the technical details and just mention one last thing, and that is that with the chessboard being so much smaller than massive images, we can actually compute the covariance between any activation in the network and the input, which is um, quite a big calculation, but it's doable because the chessboard is so small. And in this case, ignoring the technical details, this is an activation unit from block 5 in this ResNet. Specific unit that's centered around roughly over the central squares. And there are uh, uh, activations in the or units in this ResNet that only look for very, very specific patterns. For instance, there's a unit that only looks for a pair of central pawns on the e4, e5 square. Averages everything out. It fires when it sees those 2 pawns. And you actually see this pattern all the way up to the last layer because it needs to know where the pieces are. So this is very similar to some of the things you can do with convolutional networks for computer vision. It's interesting to see that there are neurons that look for specific patterns. There's a lot more. So if you want to know more, there is a fun paper on arXiv called "Acquisition of Chess Knowledge in AlphaZero." If you can bear reading 60 or 70 pages, it's a fun read with tons of ideas to find out what AlphaZero is doing. Okay, in the last 2 or 3 minutes, I'll just tell you about how AlphaZero could be used to reimagine chess. This is just some creative exploration that you could do. So Vladimir Kramnik is a collaborator of ours, and he was a chess world champion a few years ago. And he has a proposition, and that is that top chess players need to memorize a substantial amount of opening theory as in initial moves. And it's possible to enhance creative play, i.e. rely less on memorization, if you tweak the rules ever so slightly. So we propose a few challenges. One is to, a few of them are to change the rules. So in this case, disallow castling, which is a very particular once-off chess move, which completely upsets the apple cart for many chess games. So what if chess evolved in a different way over 500 years? What would top-level play look like? And it turns out that you can't really answer that question with a traditional chess engine because it requires so much hand engineering and human knowledge and experience, which we don't have. But you can answer this in simulation if you have a system that trains itself to like a superhuman great level. So in the last 2 minutes, I'll just say, what if you make some atomic rule changes? So I'll just mention a few. So what if a pawn can move 2 squares? Always, for instance. Or what if a pawn can move backwards? Or what if pawns can move sideways? Or what if you can capture your own pieces? Would all of these things change the dynamics of the game or not? In simulation in AlphaZero, you could show that there are variants of chess that will be a lot more decisive than the current classical game that we know. So for instance, if we look at a chess variant where you move your pawn, which is the smallest piece, 2 squares forward, always, as an option, that is a lot more decisive than what we know as a classical game. However, if you could only move your pawns 1 square at a time, that game becomes really drawn very quickly. So chess opening theory changes. There's some openings that will just become completely dumb under a minor rule change. For instance, I'll skip these slides and just get to the end here, and that is that in the same way that we could tell what the relative piece values would be for classical chess in AlphaZero by regressing, we could also tell what the relative piece values should be. We can distill it out of the network for all sorts of tweaks and changes to the rules of chess. And there are versions like classical chess in the top row, where your queen's worth 9 pawns or 9 points. And then if you change the rules where the pawns could move sideways as well, the pawns become these superpower pieces just by the small adjustment. The queens become less important, etc. So you can guess what the game dynamics would be just by looking at AlphaZero simulation. So there's also an archive paper that's called Assessing Game Balance with AlphaZero. If you're keen to read 100 pages, don't find that boring. You could Google that and go and find it. So this is the end. I've given you a tour of the history of AI from the 1770s, with humans hiding in manual boxes playing machines. I've told you about the post-World War era with Claude Shannon thinking about how to build chess engines with Minimax search. I've told you about Alan Turing's great ideas, some of which aren't even realized yet. I've told you about Garry Kasparov losing to IBM Deep Blue. I told you about the Lisa Dahl match and AlphaGo. And then what's next? Who knows? And this is MoroccoAI community. This is where the torch is in your hands, the ball is in your court, and the floor is yours. We're looking to you to write the next chapter in AI and chess and its development. Thank you very much.
Thank you very much. Thank you very much, Ulrich, for this wonderful talk. And it was very passionate and very interesting. And I've always been interested by Go and chess, but I'm afraid AlphaZero outplayed me back in 2017, since I'm really bad at playing any of those games. So thank you very much once again for your presentation, for accepting our invitation, and for the amazing talk that you have given.
Thank you everyone for hosting me. It's really nice to see you remotely this morning.
So see you very soon.
Bye-bye.